Hey guys, welcome to Material and Energy Balance NKB 10704, and I'm Salihin and I'll be mentoring you throughout this paper. So this paper is for ICO students, and I'll decide in making a video podcast for this paper in general for the idea so students can watch it later again and again to sharpen their knowledge, or if they forgot some of the terms or something, they can watch it again and learn it again. So I decide to make both lectures and tutorials as a podcast. So after I make this, probably I'll upload it into YouTube so you can watch it later. So as a start, this is the textbook that we'll be using. It's an elementary principle of chemical processes by Richard Felder. Yeah, this textbook is quite good, and if you're buying it, I think the price is about 110 ringgit, and you can use it throughout the whole 4 years of studies here. Alright, I think that's for introduction, and let's get started with the first chapter. Alright guys, this is chapter 1, Introduction to Engineering Calculation. So this one is the lecture slides, and I'll be going back and forth between the lecture slides and the textbook. I'll be using mostly the red textbook, which is Felder. And yeah, so chapter 1, Introduction to Engineering Calculation. So let's go to the textbook, and here is the content for the textbook. For chapter 1, we'll be covering some of chapter 2 and some of chapter 3. So chapter 2 in the textbook is about Introduction to Engineering Calculations, while chapter 3 is about processes and process variables. Let's go back to the lecture slides. So the outline of this chapter is, first is units and dimensions. Second one is conversion of units. The third one is dimensional homogeneity and dimensionless quantities. And the last one is process variables. So let's look at the first chapter. So guys, here in the textbook on chapter 2, Introduction to Engineering Calculation, we won't cover all subtopic in the textbook, but it's a good read if you want to read it mostly, and you can use it as extra studies to sharpen your knowledge. So start with Introduction to Engineering Calculation, and so let's start with units and dimensions. So this is on page 8. So units and dimension in the page 8 is a measured or counted quantity that has a numerical value and a unit, whatever they are. It is useful in most engineering calculation and essential in many. So let's say you have two of what, so that's the numerical value, and meters, so that's what they call a unit. So that's the same with second, kilograms, gold. And next is numerical value. So is here the numerical values of two quantities may be added or subtracted only if the units are the same. So we can see it here, centimeters and centimeters, which is length is end up with 2 centimeters, while centimeters and millimeters is is not the same numerical values. Yeah, you can change it to the millimeters to centimeters, but we can discuss that later. And the third part is the numerical values and their corresponding units may always be combined by multiplication or division, such as Newton, which is force, times by length will provide a Newton meter, while kilometers divided by hour, which is length divided by time, will produce a velocity, and while kilometers divide the velocity multiplied by time will end up with length. It's so on and so on. And the last part is dimension. A dimension is a property that can be measured, such as length, time, mass, or temperature, or calculated by multiplying or dividing other dimensions, such as length over time, volume, which is length times length, and the density, and so on and so on. So that's the dimension. So let's look for other examples, which is mass over mass, which is a dimensionless quantity. Yeah, I guess that's for units and dimension, and let's look for conversion of units. So I might pause it for a while here. So we're back at conversion of units. So conversion of unit, well, that's basically converting units. So let's say 1 centimeters to 1 millimeters, 10 millimeters, sorry, to 10 millimeters equal to 1 centimeters. So that's the conversion of units. So it says here, to convert a quantity expressed in terms of one unit to its equivalent in terms of another unit, multiply the given quantity by the conversion factor. Let's say, for example, to convert 36 milligram to its equivalent in grams, so 36 milligram divided by 1,000 milligram equal to 0.036 gram, which means 1 gram equal to 1,000 milligram. So since we have 36 milligram, so that's end up as a 0.036 gram. Yep, so that's the basic of conversion of units, and since there's an example here, let's just look at the example. So the example is convert an acceleration of 1 centimeter second square to its equivalent in kilometer per year square. So is this acceleration, so it's length over time square. So we want to convert 1 centimeter square to kilometer per year square. So we start is 1 centimeter per second square, and so this is 1 second square is so 3600 second square is equal to an hour square. Wow. And then we move progressively. 24 hours square equal to 1 day. So the next is 365 days equal to 1 year. So you can see here from second to hours to day and to year. The next is to change the centimeter into kilometer. So you can see here 100 centimeters equal to 1 meters, while 1,000 meters equal to 1 kilometers. And with that number, with these numbers available, you can arrange it like so, and convert it to kilometer per year, and you get 9.95 times 10 to the power of 9 kilometer per year square. So this is acceleration. I'm not sure that's the acceleration of light. I think light is a lot and a lot and a lot bigger. So I guess that's for conversion of unit, and we'll go to the system of units later. The next part of this topic is systems of units. So for this part, we can say that the components of units, there's 3 here. So the first is base unit, which is for mass, length, time, temperature, electrical current, and light intensity. The second part is the derived units, which is obtained in 2 ways. The first is multiplying and dividing base or multiple units, such as centimeter square. So this is you multiplying length over length, while feet over minute is dividing length over time, while kg/m over s square is multiplying mass with distance and divided by the square of time. Derived units of this type are referred to as compound unit. The other one is it's I don't know what they call it, as defined equivalent of compound units. For example, 1 pound, 1 foot-pound equal to 332.174 pound times feet divided by second square. Well, then the other one is 1 ERG, 1 erg. I have no idea what this is about. But anyway, so 1 erg is equal to 1 gram centimeter over second square. So that's derived units. The last part is multiple units, which are defined as multiples or fraction of base units, such as minutes, hours, and millisecond, all of which are defined in terms of the base unit of a second. Multiple units are defined for convenience rather than necessity. It is simply more convenient to refer to 3 years than what is this? 94,000. So no, that's 94,608,000 seconds. So it's better to call it 3 years with multiple units. Yep. And next is what they call it SI system for short, which is the name is the Système International des Unités, whatever it is, probably French. Go and ask MFI how to pronounce it. I have no idea. Sorry about that. So this SI unit, let's just call it SI unit, has gained widespread acceptance in scientific and engineering community. We use this a lot. Let's say base SI unit, ampere for electrical, and candela for intensity. Oh, and it does say we will not concern us in this book. So SI, let's say second, meters, and etc. That's the prefix of that. Watt, we use watt. And my mouse is getting crazy. The next is the CGS system, which is, they say it's almost similar to SI, except they use grams and centimeters instead of kilograms and meters. So SI, they use kilogram and meters, while the CGS system, they use grams and centimeters. So the other part is American engineering system. So I guess American engineering system, they use this in America, or they call it the USA. I have a friend that studies in Canada, but they're still using the SI system. So I guess American use this, and I'm not sure if UK use this or not. I think French also use this synonym, American engineering system. I'm not sure, you have to check it. So the base unit for American engineering system are foot for length, which is FT, and 1 pound, which is LB, still second for time. So it says here, this system has two principal difficulties. The first is the occurrence of conversion factors, which is weird, such as 1 feet is 12 inch, so 12 inch equal to 1 foot, which unlike those in metric system, is not multiple of 10, such as 10 centimeters, 10 millimeters equal to 10 centimeters, 100 centimeters equal to 1 meter, and 1,000 meters equal to 1 kilometers. So that's weird. Yeah, so that's the three different part, which is SI unit, CGS system, and American engineering system. And you can see in page 11 that's give the base unit and derived units. So the base unit is length, mass, mole, time, temperature, current, and intensity, while the derived unit is volume, force, pressure, work, power, and all those. You find it later. Well, the middle part is multiple unit preferences. So I guess students who profound with electronics or gadget usually good at this, because you know the megabyte race, the gigabyte race. So 1,000 kilo is 1 mega, while 1,000 mega is 1 giga, while 1,000 of gigabyte is equal to 1 terabyte. Well, equal terabyte is you know, the computer system thing. Yeah. So you can go smaller, which is a centi. So this is based on meters, based on SI. So 1,000 meters is 1 kilo, and 100 is a centi. 1/1,000 is millimeters, and then 1/1,000 millimeters is micrometers, and 1/1,000 micrometers is equal to nanometers. Yep. So yeah, that's basic. You do all the calculation and you might remember all this. So is there any example? Yeah, we can do one example for this. So conversion between systems of units. So the question is, convert 23 pound-foot over minute square to its equivalent in kilogram centimeter over second square. So here is the workflow. So the result is from 23, it will end up to 0.088 kilogram centimeter over second square. So how do they do it? So they use the conversion factor, as we discussed before. So 1 pound, a pound is equal to 0.45353 kilogram. Yeah, it's weird. So you can just say a pound is equal to 0.45. So usually 1 kilogram is about 2.3 pound. So that's for pound, and that is for a foot. They use it slightly different here. So for 100 centimeters is equal to 3.281 foot. So if you remember in SPM, they said 30 centimeters equal to 1 foot. So as we discussed before, 1 foot is 12 inch. So I think an inch is about 2.5 centimeters. And let's go to time. So here is the time. So for this, a minute is equal to 60 seconds. So since it's a square here, so you add up the square on each side. So yeah, the idea here is the calculation, and that's your answer. So as easy as that. So they say here, cancellation of units, leave kilogram over centimeter, kilograms times kilogram centimeter over second square. So how the cancellation of unit? Because the conversion factor. So since a pound is up here, so they put a kilogram up here and while the pound down here. So 0.45 kilogram to 1 pound. So they cancel out pound and leaving out kilogram. And then since the foot up here, they put it down there, and you can cancel it out. So that's kilogram centimeters. So since minute at the bottom, they put the conversion is 1 minute to 60 seconds. So they cancel out the minute and leaves out seconds square. So in the end you get this amount of, so in the end, so 23 pound foot per minute square is equal to 0.088 kilogram centimeter of a second square. So that's how it was done. Now let's move to the next section. Hey guys, let's discuss on scientific notation and significant figures. So for the first is about scientific notation. So when a number is expressed as a product of another number and a power of 10, it is referred to as scientific notation. So you can see here, so this is 2300 and its scientific notation is 2.3 times 10 to the power of 3. So that is scientific notation. Now let's discuss about significant figures. So the significant figures of a number are the digits from the first non-zero digit on the left to either A, the last digit, 0 or non-zero on the right if there is a decimal point, or the second one, the last non-zero digit of the number if there is no decimal point. So the key point here is the decimal point. Oh, something just fell. Never mind. Now let's look at the examples. So this is 2300 and 2.3 times 10 to the power of 3. So since 2300 has no decimal point, so the significant figures is the last non-zero digit of the number. So the last non-zero digit is 23. So there's only two numbers there. So for this term, it has two significant figures. So for the scientific notation, it's 2.3. So that's a decimal point there, and it's still two significant figures. Let's look at the second example. So this is 2300 and there's a decimal point at the end there. So since there's a decimal point, it has four significant figures, and it's the same with the scientific notation, which at the end it says 2.300. So it still has four significant figures, and so on and so on. So since there's a decimal point there, so even though it's a 0, so this number has 5 significant figures, and it's the same with the scientific notation. So that's 5 significant figures. And another example is here. So 23,040. So since there's no decimal point, it's only 4 significant figures. So the same also follows for the other two samples, which has 2 significant figures, and the last one has 4 significant figures. Let's move to the next slide. And we're still discussing about significant figures. So here we discuss about When two or more quantities are combined by multiplication and or division, the number of significant figures in the result should equal to the lowest number of significant figures of any of the multiplicants or divisors. So it says is equal to the lowest number of significant figures, so that's the key. So let's look at the example. So 3.57, so that's three significant figures, and times by 4.286 with four significant figures equal to 15.30102. So that's 7 significant figures. So since we use the lowest number of significant figures of any of the multiplicants or divisors, so this is a multiplication, so we use the lowest number, which is 3 significant figures. So in the end, 15.30102 just become 15.3 because we are using the lowest number of significant figures in the first part, which is the multiplicants. It's hard to pronounce it. Anyway, let's look at the second example. That's a long one. So this is both multiplication and division. So the first part has what do you call this? Anyway, let's move on. So it's 5.2 times 10 to the power of negative 4 times 0.1635 times 10 to the power of 7 divided by 2.67. So there's two significant figures there, and 0.1635 has four significant figures, while the division section has three significant figures. So I guess you can guess what's the end significant figures. So it has to be two significant figures because that's the lowest number of significant figures in the multiplication and division. So in the end, the answer is 318.426966, and you can have two solution with it, which is 3.2 and times 10 to the power of 2, which still stand for two significant figures, or it's 320, that still stand for two significant figures. Alright, I'm just checking what's scientific notation. Yep, so we're discussing about scientific notation. That's what I forgot there. I'm old. Alright, then let's move to the next section, and still significant figures. And now is, we discussed before, is multiplication and division. Now we discuss on addition and subtraction. So the term here, when two or more numbers are added or subtracted, the position of the last significant figures of each number relative to the decimal point should be compared. So of these position, the one the farthest to the left, so the one the farthest to the left is the position of the last permissible significant figures of the sum or difference. So I don't know how to explain this, so let's let's explain it. I'll explain it through the example. So let's say use the first use the first example. So 1.0000 plus 0.036 plus 0.22. So in the end, the answer is 1.2560. So since it says the one farthest to the left is the position of the last permissible significant figures. So here is two significant figures. Oh no, that's not two, that's 5 significant figures, and here is 3 significant figures, and 0.22 is 2 significant figures. So 0.22 is the farthest to the left of the decimal point. So here we only use up to 2 decimal point. So here is the original answer is up to 4 decimal point. So in the end we only use 2 decimal point. So 1.2560 become just 1.26. So just remember to round up 5 to 6 because here is 6, which is more than 5, Swedish rounding. Let's look at the other example here. So it's 2.75 times 10 to the power of 6 plus 3.400 times 10 to the power of 4. So we end up rounding it to the power of 6, everything to the power of 6. So it end up 2.75 plus 0.03400. So I guess they're keeping it to 4 significant figures here. So for the decimal point is 2.75, so that's 2 decimal point, while here at the end is 5 decimal point, or 6, 2, 4, 5, or it's 5 decimal point. So the answer is 2.784 times 10 to the power of 6. But since they only using it to 2 decimal points, so it's end up the final result is just 2.78 times 10 to the power of 6. So that's how for addition and subtraction. And that's all for significant figures and scientific notation. I keep forgetting scientific notation. Oh, I'm old. Anyway, that's all for scientific notation and significant figures, which is about multiplication and division, subtraction and addition, and how to determine the amount of significant figures in a number. Alright, that's all. What up, guys? So now let's talk about dimensional homogeneity and dimensionless quantities. First, let's discuss on dimensional homogeneity. So on the first note here, every valid equation must be dimensionally homogeneous. That is, all additive terms on both sides of the equation must have the same dimension and consistent units. So basically, we can say the left side and the right side of the equation must have the same units. Let's have a look at an example. So this example is, I took it from the textbook, and it's example 2.6-1. So, consider the equation d equal to 3t minus 4. So, the left side, which is d, is in foot or feet, and it's equal to 3t minus 4. So, for the first question, for the equation to be valid, what is the dimensions of the constant 3 and 4? So for 3, we know that for to be homogeneity, which is to get the left side and the right side to be equal, so 3t must be in the concept of length, so which is feet here. So t is in second, so for the constant 3 to be in feet, it must have the dimension of length and time. So you can see in the solution here, so the constant, let's just do like this. So the constant 3 must therefore have the dimension of length over time, which is multiplied by time itself. The time will cancel out, leaving the length only. So the right side will be equal to the left side, which is feet. And for the constant 4, since there's no other multiplication or division, so the dimension is easily the length. So if the equation is consistent with its unit, what are the units of 3 and 4? So for consistency, the constant is of 3 is 3 feet per second, and for constant 4 is 4 feet, to get the dimensional homogeneity of the right side, the left side, sorry. So what's the third question? The third question is, derive an equation for distance in meters in terms of time in minutes. So how to do this? Well, so back to the question. Here you are. So define the new variable d in meter and t in minute. So the initial part is d is in feet. So we just have to change the feet to minutes. So in the end, at the first part, for d to be in meters, so we have to convert from feet to meters. For 3.28 feet equal to a meter. So in the end, d is equal to, so the new constant is 3.28 d hyphen, or whatever they call it that. And for time, the first is in second, so to change it to minute is the easiest part, is 60 seconds equal to a minute. So it end up with 60 t. So after the substitution, d equal to 3t minus 4 equal to 3.28 d hyphen equal to 3 times 60 t hyphen plus 4. And then we simplify it by dividing through 3.28. In the end, we get d equal to 55 t hyphen plus 1.22, which is now d is in meters and the time is in minutes. Yep, so that's the question, the examples, and I guess that's all. Alright, so let's look back at the outline and look on what we have covered. So far we have covered units and dimensions, conversion of units, dimensional homogeneity, and dimensionless quantities. And I think I forgot to mention about dimensionless quantities before, and let's just go quick on dimensionless quantity. So dimensionless quantity is, let's say you divide something like length over length, so the length is cancelled out, so in the end you get a dimensionless quantity, which basically a ratio of length. So yeah, as simple as that. Alright, so let's now go to the process variables. And process variables in the textbook is on chapter 3. Alright. Now let's look at process variable section, and first we will discuss about density, and next is specific gravity. So we'll discuss these two. So mass and density. So basically everyone knows mass. Now we just discuss about density. So density is the mass per unit volume of a substance. So it's represented by P value or rho, and M is mass, while V is the volume, so mass per unit volume. And you can use it, the mass flow rate and the volume flow rate. So the flow rate will cancel out each other, and in the end you just get the density. And let's look at an example. Probably, let's say, so we use this. The density of a substance can be used, don't forget about that. For example, the density of carbon tetrachloride is 1.595 gram per cm cube. So the mass, so find the mass of 20.0 cm cube of this carbon tetrachloride. So since they give us the, what was this, the density, and so the density, so the density is 1.595, so you can multiply it with the mass of carbon tetrachloride, and it will, the mass, the, no, not the mass, this is the volume of carbon tetrachloride, sorry. So the volume will cancel out with each other, and in the end the product will be the mass of carbon tetrachloride. So we can say that in 20 centimeter cube of carbon tetrachloride, it weighs 31.9 gram. So that's how you find the mass of a substance using their density. Alright, let's get back to the slide. The next is specific gravity. So here it says specific gravity, or SG, is the ratio of the density of the substance to the density of a reference substance at a specific condition. So it says here ratio. So I guess we can get back to the dimensionless constant or quantity, whatever it is. So that's the ratio. So specific gravity equal to the ratio of the density of the substance to the density of the reference substance. So density of a density equal to no units at all. So the reference substance is H2O liquid at 4 degrees C. So that's at a specific condition. So for water, for liquid water, water is always liquid, right? The other thing is ice. So let's get back to it. For water in liquid at 4 degrees C, its density is 1 gram over a centimeter cube, or 1,000 kilogram over a meter cube, or 62.43 pound per cubic foot. So I guess that's the acronym foot. I think a singular they call it foot. If it's plural, it's feet. I have to check it back. I'm old. So yeah. So what does it says? SG is 0.6 on 20 degree over 4. No idea. I get back to that. So let's look at an example. I think it's down here. Yep. So that's it. What is discussed before. So the notation of 0.6 20 over 4 signifies that the specific gravity of a substance at 20 degrees C with reference to water at 44 degrees C is 0.6. So we can say that if this is reference is 1, so on the top here the P is 0.6 because it's 0.6 to 1 is 0.6. Duh. Right. Let's look at an example. I'm stuttering now. Yeah, this will do. Oops. So mass, volume, and density. Example 3.1-1. So the question is, yep. Oops. Can you see it? I guess you can see it. Calculate the density of mercury in pound per cubic foot from a tabulated specific gravity and calculate the volume in cubic foot occupied by 215 kilogram of mercury. So they say is in table B1. List the specific gravity of mercury at 20 degrees C as 13.546. So that's the SG of mercury, 13.546. Table 1 is in the book, at the end of the book. So I guess that's another reason for you to buy the book. 120 ringgit, I think. Go and buy it. So arranging the equation, the SG equation up here. So you have to arrange this equation equation 3.1-1, you have to arrange it and to get the density of a mercury. So this is the Sg, and since they use in pound per cubic foot, so we use the third reference and multiply it, you get 845.7 pound per cubic foot. So that being done, or that being said, now we can find the volume of the mercury that occupied by 215 kilogram of mercury. So we can use this solution here. No, we have to use this solution here. The solution was prepared. So for 215 kilogram, change it to pound. So a pound equal to 0.454 kilogram, and we can multiply it by, what's this? So this is the inverse of the density of the mercury. So yeah, so that's the inverse. A cubic foot over 845.7. Why do we inverse it? So in the end, we want a cubic foot, which is the volume of the mercury. So we can inverse it, so we can cancel out. So 215 kilogram will cancel out with the conversion factor of kilogram to pound. And then the conversion of pound, it can cancel out with the conversion with the density value. So in the end, you'll get the amount of volume of the mercury. And in the end, with this equation, you finally get 0.567 cubic foot of mercury occupied by 215 kilogram of mercury. So yeah, that's how you calculate it. You have to change the equation, not change the equation, you have to manipulate the equation to get the volume, the mass, or the density using the specific gravity. Alright, that's all. So now let's look at chemical composition, and we start with mass and mole fraction. So a composition of a mixture can be defined as one is the mass fraction and the other one is mole fraction. So mass fraction is mass of something over the total mass, while the mole fraction is the mole of something over the total moles. So for the mass and mole fraction, the units need to be the same. Let's say 0.25 kilogram of something over the kilogram of total mass, or 0.25 mole of something over a total mole of something. So let's say the first thing is kilogram over kilogram, and mole over mole, kilomole over kilomole. So yada, so on and so on. Now, still mass and mole fraction. Let's say you want to change a mass fraction to a mole fraction. Yes, you can do that. So at first, you have to assume the mass as the basis of calculation of the mixture, since you want to change from mass fraction to mole fraction. So using the known mass fraction, you can calculate the mass of each component. And then once you get the mass of those components, you can convert those masses into moles. So mass to moles, that's SPM. And then you can take the ratio of those moles of each component to the total number of moles. So as we discussed before, is moles, mole fraction is mole of something over the total moles. So from mass fraction is mass of something to the total mass. So basically you find the mass first, you find the mass of each components, you add up of all those components and you get the total mass. And you can change it to moles too from mass fraction. So you have to assume the mass as the basis first. So that's the SOP to convert mass fraction to mole fraction. And if you want to convert mole fraction to mass fraction, you just use mole fraction as basis, then find the mass of each component. Find the moles of each component, convert the moles to mass, and use the mass of each component, add it up to get the total mass, and you get the moles fraction. Yeah, so you just change it around. Alright, so that's mass and mole fraction. So we've covered the first part of chemical composition, which is mass and mole fraction. Now let's look on the average molecular weight calculation. So, well, the average molecular weight is like what you said, the average of component. Well, that's not component. Let me rephrase it again. Let's say you have a mixture of component in a solution or air, so you can average the molecular weight. You can calculate the average, the weight of all those molecules in a mole or kilomole of solution. Yeah, so yeah, that's close enough. So there's two types to calculate, which is from the mole fraction and from the mass fraction. So if you have a mole fraction of the components in a mixture, so you can use the first calculation, first formula. And if you have a mass fraction, then you can use the second formula. So in the book, the formula is on page, what page is this? Page 51 up here. Yeah, so it's the formula of 3.3-7, and the second formula is 3.3-8. So let's have a look at an example. And example 3.3-4. So the question is, let me use my tablet here. So calculate the average molecular weight of air from its approximate molar composition of 79% of nitrogen gas, which is N2, 21% of oxygen gas, which is O2. So that's approximate molar composition. Molar composition. So in molar composition is 79% to 21%, while the mass composition is this part, 76.7 to 23.3%. So let's consider the first equation first. And from equation 3.37, So you get the fraction, the mole fraction of nitrogen is 79%, 0.79, and the mole fraction of oxygen is 0.21%. So from the equation, the average molecular weight is the mole fraction of nitrogen times the molecular weight, I think, which is molecular weight of nitrogen plus the mole fraction of oxygen times the molecular weight of oxygen for 1 mole or 1 kilomole. In this equation we are using kilomole, which is 1,000 mole. So the first part is you have to multiply the fractional mole fraction multiplied by the molecular mass of nitrogen gas, which is 1 kilomole of nitrogen gas weighs in 28 kilogram, and you times it by 0.79, which is 79%. And next is the same thing to oxygen gas. So in the end, with this formula you'll get 29 kilogram per kilomole, which means per kilomole of air you get it weighs 29 kilogram. So if you convert it to pound to mole, you get this amount of value, 29, and 20, and you can convert it directly to gram per mole, which is everything in kilo. So that's a multiplication of 1,000. So let's look at equation 2, which is we're using the mass fraction in here. So nitrogen is 0.767 gram of nitrogen per gram of gas. So you divide it by its mass fraction, not mass fraction, oh my god, molecular weight. What did I call it just now? Whatever this is. So it's 28 gram of nitrogen gas per mole of nitrogen gas, and you add up with the same equation for oxygen, and you get the amount of 0.035 mole per gram. But since we want a average molecular weight, so the equation stated is 1 over average molecular weight. So for average molecular weight, you change it and you get 29 gram per mole. So it's the same thing with using the the first equation, which is so since the first equation uses a kilogram or kilomole, while this is gram per mole, you can see it's the same thing. Never mind. Select tool. Alright, so that's about molecular weight, average molecular weight. So we'll move on to the next topic. So the last part for chemical composition is about concentration, and after that is ppm and ppb, which stands for parts per million and parts per billion. So let's look at concentration. So concentration can be divided to 3 parts, I guess. So the first part is mass concentration, second is molar concentration, and the third is molarity. So mass concentration of a component is the mass of this component per unit volume of the mixture, while the molar concentration is the number of moles of the component per unit volume of mixture. And molarity is the value of molar concentration expressed in mole per liter. For example, 2 molar is 2 mole per liter. So if someone asks, can I get a 5 molar HCl? So that's 5 mole of HCl in a liter of solution. And the next part is part per million and parts per billion. So the units ppm or ppb are used to express concentration of traces species, which is a very rare species to be traced. Let's say, what what's an example that I could think of is heavy metals or precious metals. Yeah, I'm stuttering just now. Sorry for that. So for the part is, let's say yi is the fraction of component I. So parts per million, yeah, million is 6, 10 to the power of 6, while billion is 10 to the power of 9. So if the component is a lot more, is abundant, quite abundant, you can use parts per million, while if the component is rarer, you can use parts per billion. You get it? Right, let's just go through on the textbook. So on page, what's the page? Page 52 and 53 explain about concentration and parts per million, parts per billion respectively, and there's few examples there too. So I guess, well, concentration is your SPM and your prep studies, while parts per billion, parts per million and parts per billion is relatively easy. You just convert it to 10 to the power of 6 and 10 to the power of 9 for parts per billion. Yep, I guess that's for chemical composition, and we can move to the next topic. I think it's about pressure and temperature. Hey guys, so the next part of process and process variables is pressure. So now we're gonna discuss about it. So in pressure, we will discuss about, well, the pressure, and the next is some pressure measuring devices. So let's start with, well, the term pressure itself. So in the textbook is on page 54. So that's the definition of pressure, is the ratio of force to the area of which the force act. So in the end, the force over area means Newton over meter square, or they call it, dyne over centimeter square, and pound force over inch square, or in the end they call it PSI or Pascal. In SI, yeah, so in SI the pressure is called Pascal, so PA. You found this a lot in petrol station on kPa to pressurize your car tires or motorcycles or bicycle. So that's define pressure, and now let's look at hydrostatic pressure. So the pressure of fluid at the base of the column, so at the base of the column, is called hydrostatic pressure. And let's say by definition is the force exerted on the base divided by the area. So my mouse is crazy. Anyway, so the total pressure is P equal to P naught plus rho GH. So I guess P naught is the atmospheric pressure and rho GH is the hydrostatic pressure, which in total add up to provide the total pressure at the base of the column. So rho GH is not the hydrostatic pressure. The P is the hydrostatic pressure, and rho GH is the addition pressure for the to find the hydrostatic pressure. Correct me if I'm wrong. Anyway, now let's go back to the lecture slides, and so there's also hydrostatic pressure in the lecture slide. You can, well, that's just basic. Rho GH is the terms for pressure. And let's look for the pressure measuring devices. And let's look at the image. So this is a gauge, or they call, I don't know, what do you call it, gauge? I think they call it gauge. So this is a Bourdon gauge, and another type of pressure devices is manometers. So there's three type of manometers, which is the open end, differential manometers, and the seal end manometers. So you can use you'll find all of these type of manometers throughout industry, but most pressure measuring devices they use a gauge. So this is an example of Bourdon gauge. You find this a lot at the top of the container, what they call the liquid container, like gas container, oxygen container, what other container, nitrogen container. So let's get back. So to find the absolute pressure, you must add the value of the gauge pressure, which is the reading on the gauge itself, and you have to add up with the atmospheric pressure. So that's become the absolute pressure, the pressure of the tank or the area itself. So you have to add up both gauge and atmospheric pressure. And to get to know what is atmospheric pressure, let's just go back to the textbook, and I think there's in here somewhere. And hold on, it's on page 54. No, it's not on page 54, it's on page 56. There you go. So a typical value, so a typical value of atmospheric pressure at sea level is 760 millimeter of mercury, and has been designated as a standard pressure for 1 atmosphere. So at the front of the book, there's the conversion table to find the pressure on various situation. So here it says the fluid pressure referred so far as the all absolute pressure. So the absolute pressure here, and the pressure measuring devices give the gauge pressure. So to find the absolute pressure, you have to add up the gauge and the atmospheric pressure. So if the gauge shows 4 atm and the atmospheric pressure is 1 atm, so the absolute pressure is 5 atm. So that's using the gauge pressure. And next is about the manometers. So that's the manometers that I showed you before in the lecture slides. Is basically a copy and paste from the book into the lecture slide. I don't make the lecture slide, someone made it. Well, someone has to be lazy. I'm lazy too. Never mind. So that's the general manometer equation, and that's the differential manometer equation. And in the end, the equation that we use is mostly this one and this one. Well, mostly this one, because this is they give the numbers in here, so we're gonna use this. And then let's look at an equation. Not equation, example. Oh my lord. So example 3.43, number 1. So the question is, a differential manometer is used to measure the drop in pressure between 2 points in a process line containing water. The specific gravity of the manometer fluid is 1.05. The measured level in each arm are shown below. Calculate the pressure drop between points 1 and 2 in dynes over centimeter square. So they want it in dynes, not in kilogram over meter square. Or what is this? Not in SI units. Anyway, so that's the solution. Oops. So they use the equation 3.46, which is equal P1 minus P2, which is the difference in pressure, the pressure difference. So that's the density of fluid minus the density of water, I guess, times the acceleration and the height difference, which is, that's the height difference before, 382 minus 374. So so it says here 382 minus 374. So we calculate the difference in, what do you call this, density. So 1.05 minus 1 gram over centimeter cube. Does it say here? So that's the density of the fluid, and this is the density of water. So processing line containing water. So water is 1 gram over centimeter cube, while the fluid is 1.05 gram over centimeter cube. So this one represent this one. Yep. And guess what is this one? So 980.7 centimeter over second square. So that's acceleration. So this is the acceleration of gravity of the gravity pull, which is 9.81 meter per second square, which convert to centimeter is 980.7 centimeter over second square. Alright, so let's forget about dyne first, and not dying. let's consider the height difference. So the height difference is 8 millimeters before, so 8 millimeters. So for dimensionless homogeneity that we discussed before, so we have to change the millimeters to centimeters. So that's the factor. So 1 centimeters equal to 10 millimeters. So that's cancel out, the millimeters cancel out to produce, making it 0.8 centimeters. So if you forget about this value, you get the amount, the what they call the pressure difference, which is in, let's say, centimeter, which is gram over centimeter second square. So it just convert it to dyne over centimeter square using this conversion factor, which is the same thing actually. Never mind. So in the end you get 40 dynes over centimeter square. I do believe it still be 40 gram centimeter over second square. If anyway, all right. So yeah, that's the pressure covered. So let's move to the next topic. So guys, this is the last part for chapter 1. Yay! And it's about temperature. So basically it's more about knowing what type of temperatures and the conversion factors, conversion units required to convert all these temperature scales. So in here we can describe that for temperature we have Kelvin and Celsius, while the other one is Rankine, denoted by R, and Fahrenheit. So from Celsius to Kelvin, so Kelvin is, so 0 Kelvin is basically an absolute zero, so which is minus 273.15 Celsius. So for if the temperature is recorded at 1 Celsius, so for Kelvin is 274.15 Kelvin, and for Fahrenheit is dependent on Rankine too. So 0 Rankine is minus 459.67 Fahrenheit. So you have to add up Fahrenheit to obtain Rankine temperature. And from Rankine to, hold on, my mic, oops, not my mic, my mouse died on me. So to convert Rankine, to convert Rankine to Kelvin, it's 1.8 of Kelvin. So 1 Kelvin equal to 1.8 Rankine. And for Fahrenheit to Celsius is, if you have 1 Celsius, so you have to times by 1.8 plus 32 to get the Fahrenheit. Fahrenheit is usually used in baking and your body temperature. I think the normal body temperature is 95 or 97 Fahrenheit, and for baking is normally 250, I think 400 Fahrenheit. And yeah, so you have to times by 1.8 and 32 plus 32. So here is the conversion factor of this temperature. So Fahrenheit to Celsius is 1.8, Rankine to Kelvin is 1.8, Fahrenheit to Rankine is 1 to 1, so the ratio is 1 to 1. Celsius to Kelvin is 1 to 1, so you just need to remember 1.8 to 1 for Fahrenheit to Celsius and Rankine to Kelvin. So guys, I guess that's all for this chapter 1, and yeah, that's it. We are done for chapter 1, and go and do a lot of assignments, exercise, and yeah, I will provide tutorial for this chapter too. All right, thank you.